Good evening, everyone. My name is Ansar, Triple Department, St. Peter's Engineering College. Today I am discussing about time domain analysis. Introduction. In time domain, whenever we are going to discuss about a time domain analysis, for any system we are having two types of times. First one is transient time period and steady state time period. In time domain analysis is nothing but the response of a dynamic system to an input is expressed as a function of time. It is possible to compute the time response of system in the nature of input, and mathematical model of the systems are known. Here, when we are going to find out the transient response or steady state response is nothing but if you know the input, for input which signal you are giving. Which signal means there are different types of signals we are having. That signals we call it as a standard test signals. In the standard test signals, we are having different types of standard test signal: impulse signal, step signal, ramp, and parabolic signals. The characteristics of actual input signals are a sudden shock, sudden change, constant velocity, and a constant acceleration. Here the sudden shock is nothing but we call it as an impulse response. Sudden change is a step signal. Constant velocity is a ramp signal, and constant acceleration is a parabolic signal. By using these signals we can find we can judge and we compare the dynamic behavior of the system by using different standard text signals that are an impulse, step, and constant velocity and constant acceleration signals. The other standard signals are of great importance is sinusoidal signal. Apart from these test signals, we are having sinusoidal signals too. First, we need to know that standard test signal. In that part, we are having an impulse signal. Already, I told you that the impulse signal is nothing but a sudden shock. Sudden shock means it will be it will be going to be a respond when t equal to 0. It will be gives some signal of magnitude a in the remaining positions. When t is not equal to 0, this system response will be equal to 0. Only if the impulse signal response will be present only when t equal to 0. When t is not equal to 0, the delta of t it must be equal to 0. That we call it as an impulse signal. Impulse signal will be present only at time t equal to 0. In the remaining cases, when t is not equal to 0, the delta of t must be equal to 0. Next, we are having a step signal. Step signal is nothing but sudden change. It will be gives the step signal gives a sudden change characteristics of an input actual signal. Here in this diagram, whenever u of t equal to whenever u of t is equal to 0, then u of t equal to a. In the remaining position, t greater than or equal to 0, it will be equal to a. Otherwise, if a equal to 1, then the step signal is called it as a unit step signal. Similarly, ramp signal. Ramp signal is nothing but this is a velocity characteristics of an actual input signal. When t greater than or equal to 0, then only it will be going to be activate. When t equal to 0, it will be equal to 0. It will be going to be increases linearly. Next, standard parabolic signal. Parabolic signal we call it as an acceleration signal. Whenever you are going to be it will be going to be rises. Whenever when t greater than or equal to 0, it will be equal to at by 2. This signal we call it as a parabolic signal. Here the relationship between the different types of standard test signals is nothing but the integration of impulse signal will be equal to the step signal, and the integration of step signal will be equal to the ramp. Integration of ramp signal will be equal to the parabolic signal. That means an integration of 1 is t, integration of t is t square by 2, integration of t square is t cube by 3. Here similarly in the reverse manner, the differentiation of parabolic signal is ramp, and the differentiation of ramp signal is step, and the differentiation of step signal is an impulse signal. See here Laplace transform. Whenever you are going to apply the Laplace transform for an different types of signal, standard test signal is that for impulse signal Laplace transform, if you are applying, then you are getting an a. For Laplace transform of 1 is or 1 by s, or a is Laplace transform of a is a by s. Laplace transform of test signal for ramp is a by s square, and the Laplace transform of parabolic signal, that means at by 2 at by 2 is nothing but an a by s cube. Now here we are having a time response of a control system. Time response of a dynamic system is nothing but input response to an extended function of time. We have to know that how my system will be going to when I work, how much time my system will be at a transient, after how much time it will be going to when I reaches to a steady state. That thing we have to know. Whenever I am here in the input we are giving a different test signals. Just normally we know step signal, impulse signal, ramp signal, parabolic signal. Any step signal you give, then the output we are going to get something. The output will be, our main intention is that we need to reduce the transient behavior of the particular system. When we can reduce the transient behavior of the system is nothing but we have to know that characteristics of that particular transient response. And the any type of system output, the time response is nothing but an output of any system has two components. First one is a transient response, and second one is a steady state response. In a time response of a control system, transient response and steady state, in this diagram after some time it will be going to be, and for example you consider as an your desired output input is a step input. Then after some time, that means and after 16 seconds, especially in this graph, after 16 seconds it will be reaches to step response. That means a 0 to 16 second we call it as a transient response. After that we, after 16 second we call it as a step, after 16 second we call it as a steady state response. Our main intention is that we need to reduce the transient response. When the response of the system is changed from equilibrium, it takes some time to settle down. This is called as a transient response. How much time the system will be take to settle down, that time we call it as a transient response. The response of the system, after transient response is called it as a steady state response. You take any system time response, it must be having a transient response as well as a steady state response. In transient response, the time, how much time it will be take to settle down, and steady state, after transient response, the response of the system after the transient response is called it as a steady state response. Now transient response depends upon the system poles only and not on the type of the input. The transient response, that means that characteristics in coming in this lecture only we will discuss. The transient response depends upon the poles, how many poles are there, where it will be going to be allocated. It is the sufficient to analyze the it is therefore sufficient, we need to analyze that what will be happen when you are giving a step input to the transient response and a parabolic input, what we are having, and we need to examine that all the things. For so that I am considering a first order system. As of all of you know that first order system is nothing but C of s by R of s is equal to k divided by Ts plus 1. C of s by, here it is mistaken, C of s by R of s is equal to k divided by Ts plus 1, where k we call it as an a gain and T is an a time constant. How you know that whether it is a first order system or not? Always the order of an is power that will gives that either it may be a first order or second order. Here s coefficient is 1 divided by ks plus t is nothing but an a, that is an a first order. Here also I am taking an a 1 divided by 3s 3s plus 1, 1 divided 10 divided by 10 divided by, the problem overlapped here, please make it correct. 10 divided by 3s plus 1, 10 divided by 3s plus 1, here k we call it as an a gain, and 3s plus 1 means you need to take it out s common, then you are getting an a 3s plus 5, 3 by 5 you are getting, that is nothing but an a that is a time constant. Here impulse signal for first order. What is the first order signal is k divided by Ts plus 1, that we call it as a first order. Now C of s by R of s, from this transfer, from this block diagram, C of s by R of s is equal to k divided by Ts plus 1. What is the impulse signal is 1. If you are taking an a C of s is equal to R of s into k into Ts, k divided by Ts plus 1, then it will not won't going to be a change. C of s also will be equal to k divided by Ts plus 1, k divided by Ts plus 1. Then how you are going to find out that C of t? Our main intention is to find that C of t, that if you are taking out a common, then C of t inverse Laplace transform of C of s is nothing but C of t is equal to t into k into e power minus t by capital T you are getting. That is the impulse response of an a, for C here, t into k into t into e power minus t by t. For different values of k and t you are getting the response is like this. Now the transfer function of an a first order system, whenever you are giving a step signal is nothing but an 1 by s. Similarly C of s is equal to k divided by st plus 1 into r of s. In the place of r of s you need to substitute 1 by s, and you simplify that, then we are getting the expression C of s is equal to k into k divided by k into u of t. First you substitute in the place of u of s you need to substitute 1, in the place of r of s you need to substitute 1 by s, and then you compute that, then you are getting an a you see C of s is equal, what is our k divided by Ts plus 1. Can I write so that it is better? Okay. K divided by Ts plus 1 you are getting, and then you substitute 1 by s in the place of r of s, then that equation will becomes 1 by s into k divided by Ts plus 1. After 1 by s into k divided by Ts plus 1 means, after that you need to apply the partial fractions, and then you are getting the finally the C of t value is k into u of t minus e power minus t by tau. That value we are getting. After that, here see here k equal to 10 for different values here showing. For step response for 5 values, that means what is that C of t value? C of t value is 1 power 1 minus e power minus t by capital T. Whenever you are giving a step response of a first order system, then the transfer function C of t will be equal to 1 minus e power minus t by capital T you are getting, that is the response of the system. Now you take the different values of capital T. Whenever you are taking a capital T equal to T, then you are getting the response is like this. And whenever you are taking a capital T value 2T, then e power minus 2 value, that means and whenever small t equal to capital T if you are taking, then you are getting 1 minus e power minus 1. In next case 1 minus e power minus 1 by 2, 1 by 1 minus e power minus 1 by 3, like that you take that small t equal to capital T, small t equal to 2t, small t equal to 3t, like that you need to take. And then if you are drawing the graph, this graph will be like this for different types of values. For ramp signal also, for ramp signal you just substitute an 1 by s square, then C of s is equal to k divided by ts plus 1 into 1 by s square. Again you need to apply the all partial fractions, all the things. Then finally you are getting one equation, that is C of t you need to find out. C of t you are getting, this is not required for you, first order system type. That is that very simple of an first order system. First order system is nothing but C of s by R of s is equal to k divided by st plus 1. That is the standard form, where k is a gain and t is a time. Next, second order system. In a second order system, that will be depends upon that poles and zeros, location of poles and zeros. What is meant by a pole and what is meant by a zero? The poles we are getting from the denominator and the zeros we are getting from the numerator. The second order system always will be depends upon the omega and zeta value. Omega we call it as a natural frequency and zeta we call it as a damping ratio. Here see here the basic form of transfer function is nothing but omega n square by s square plus 2 zeta omega ns plus omega n square. That we call it as a basic standard test signal, basic second order transfer function. From this I am writing an 4 divided by s square plus 2s plus 4. What is the omega n square? Omega n square is an 4. From that omega n we are getting an 2. Similarly 2 zeta omega n equal to 1. From that zeta equal to we are getting an 0.5. Zeta is we call it as a damping ratio and omega n we call it as a natural frequency. For this there are different types of poles we are having. This is a second order system. C of s by R of s is equal to omega n square by s square plus 2 zeta omega ns plus omega n square. So that we are having 2 poles, minus omega n zeta plus zeta square minus 1 minus omega n zeta minus square root of zeta square minus 1. These are the two roots detection. Whenever the system is overdamped means is nothing but when zeta is greater than 1. What about the roots will be lies on the left half of S plane. In the second case underdamped, in the underdamped the first case is overdamped. Overdamped is nothing but when zeta is greater than 1. When the system has two real distinct rules. When zeta is greater than 1, the roots will be a real and distinct. Real and distinct. When zeta is in between 0 and less than 1, the roots will be a complex conjugate. When zeta is equal to 0, the roots will be an imaginary axis. When zeta equal to 1, roots will be a real but equal poles. These are the four things very important. What are the two roots? What is the second order transfer function is that omega n square by s square plus 2 zeta omega ns plus omega n square. That is that second order transfer function. For the roots of the second order transfer function is minus omega n zeta plus zeta square minus 1 omega n minus zeta square minus 1. In the first case, I am considering an overdamped system. Overdamped system is when zeta is greater than 1. When zeta value, for example, if you are taking an zeta is greater than 1, then the roots will be an a real and distinct value. If you are taking an a when zeta is greater than 1, then we call it as an that is an overdamped system. When zeta is in between 0 and less than 1, that we call it as an underdamped system. And undamped system is when zeta equal to 0, then the roots will be lies on the imaginary axis. When zeta equal to 1, both the roots are same and real also. Here underdamped system, how we are having an underdamped is nothing but when zeta is in between 0 less than 1, due to unit step signal we are having an some different time domain specifications we need to know. What is an rise time, what is an peak time, what is an delay time, and maximum peak overshoot. Here this graph shows an delay time. The delay time is the time required for the response to reach the half of the final value of the final value the very first time. The final value of the system is an a 1, but we are not going for an a 1, only 50% of the time. That particular time we call it as an a the time required to reach 50% of its final value, we call it as an a delay time. And rise time, we are having a different definitions for an a rise time. The rise time is the time required for the response to rise from 10 to 90% or 5 to 95% or 0 to 100% of its final value. That also how we are going to segregate these things is nothing but for underdamped second order system 0 to 100% rise time is normally used. For overdamped 10 to 90% rise time is commonly used. This diagram will be shows an a rise time also TR 0 to 90% or 0 to 100% or 90 to 10 to 90%. Next one is peak time. The peak time is required for the response to reach the first peak overshoot. The time required to reach the maximum peak overshoot, that we call it as a peak time. Maximum overshoot is the difference between the maximum peak value of the response curve measured from unity. The final steady state value of the response differs from unity. Unity is nothing but C of Tp minus C of infinity by C of infinity into 100. Settling time, always we are going to focus after how much time the system will be going to settle down, that we call it as a settling time. The settling time is the time required for the response curve to reach and stay within a range about the final value of size specified. In this case exactly we may not settles with an input. There may be a change, the tolerance 2 to 5% of tolerance will be there. These are the different time domain specifications. Thank you.